Welcome. So we now have a pretty good model for the SEIR model for how an epidemic could spread. And we can use it, but we need to get it to match the data of the current crisis. So what we need to do is, first of all, look at some data and then tweak our model so that it fits that data. So let's first look at some data. Okay, so here we are on the Wikipedia page covering the COVID-19 pandemic in New Jersey. All right. I think what's important to do with this model is to only try to model one location. It would be hard to model the entire world because China and Asia were hit early on, then it moved to Europe, and now then it came to the US. So what we're experiencing now is very different than, say, what Korea is experiencing right now. So we're in completely different phases of the pandemic. So we're going to focus on just New Jersey. So here we go. Let me hide my picture here and look at the webpage. So this webpage has a lot of great information about, when did the governor declare the state of emergency, where you can see that the concentrations just outside of New York City are where our state had the most infections. That's also where we have the most largest population. So this does not have the infections per person or per capita, I should say. It has just a total number of infections. So not many people live in the south of the state compared to around the New York City area. So we would expect the numbers to look very, very different. So continuing, we can, they highlight what happened during different periods of the pandemic, but we're going to keep on scrolling and we can go all the way down. We're finding out about testing and what's going on there. This is what I'm interested in, is the data. Okay, so this data is actually right from the New Jersey government. So it comes from nj.gov. So somebody has just been collating it. So it's a reliable data. I know sometimes people don't feel Wikipedia is a very good source, but they are extracting their data directly from a reliable source. So here is good data, okay? And what this data shows is the number of cases. I believe these are cumulative cases. So no one is ever off of this list. So you can see this sort of ended on May 14th. By May 14th, there were 142,000 roughly cases of COVID-19 that had been confirmed. Okay, so they can only look at confirmed cases. They also have, by the end of this, 9,946 deaths. All right. So we can actually go, instead of looking at the last 15 days, we can look at March. We can see that when we look at March, not much had happened yet. Okay, but it was ramping up. It was the exponential growth of that. We can look at April, can add that on to the March data, and we can go all the way to May. So if I scroll through this, I can see there's data available all the way from March through May up to May 14th. That's when this was last updated. So it's pretty current. Now, I do think there's an error in this. They say at the top there's a blue part for recoveries, and then there's orange is the active cases. I believe most of these cases have actually recovered at this point because this is it takes just a couple of weeks to go through being ill and recovering. So I think most of this should be blue instead of orange, right? But there are basically two numbers here. I don't know if I can highlight them. Oh, I actually can. So for every day, there are a number of cumulative cases and a number of cumulative deaths. Given that the testing was so bad at the beginning, this only keeps track of known cases. I have a feeling that the number of cases and the number of known cases were very, very different, right? Testing has ramped up significantly, so the number of known cases has been growing, in part because we've tested more, and there are more cases overall that have happened. So I believe that using the known cases data is going to lead to a lot of error in our model. But I do believe that the known deaths are actually probably pretty accurate. So what I am going to do for our model is take the number of deaths about once per week to plot some points that we can use for seeing if our model is correct or not. There's other information on this webpage. They break it down by counties, right? Here are the number of cases. Okay, you can see the number of cases simply increases because they're not taking into account people who have left. Okay, so this is simply the number of people who have ever been infected. So it looked more like our recovery curve because somebody who you only get there by being infected. So that only goes up. The next chart down here shows the new cases per day. So that was going up and is coming down. That's the good news, that the number of cases per day is dropping off, which is why we're starting to open up. We have the number of deaths that never comes down. The graph is only going to go up. But we can see if we look at the deaths per day, this is very erratic because weekend data is very sporadic. And so there's usually a weekend lull and then a surge in reporting after the weekend. So you sort of have to look at the data one chunk at a time, 1 week at a time, in order to be able to interpret anything. But it looks like our final week here is definitely lower than the week before it. So things are heading in the right direction with the number of deaths per day. Okay, so the deaths or fatalities will never come down, but if it can level off, then that means new cases aren't occurring. Okay, so there's the data we have, but I'm taking the data that we're going to use right from this chart and looking at the number of deaths because I do feel that's the most accurate on about a weekly basis. So let's switch over to MATLAB. Okay, so you can see this is where we left off in MATLAB. All right, you don't need to code all of this that I'm about to do. In fact, please don't. But what I do want you to do is have your code open, your SEIR model version 2. I'm making a data fit model here. So I've changed a few things that you're not going to do, but we're going to change parameters together. Or actually, you could just watch this video and then at the end, you're going to want these parameters in your code, all right? Because we're going to have parameters that actually work, okay? So down here, this is a key aspect of this. So if I run it right now, it will look exactly like what we had before, okay? But I've added this little bit of code in here. I took the data from that website and I've added it right here. Okay, now what this is saying is I decided that the first week where they had some deaths was about week 8 according to our calendar. We're assuming intervention began around week 8, which is when there were 11 deaths, all right? Week 9, that's what this pair of data is. It's going to be a row of data. 9 would be the week number, and 108 is the number of deaths at that point, 10 and 537, and so on until we get up to week 16, where there were 9,946 deaths, all right? So that's all the data we have, all right? We don't know what happens beyond that because it hasn't yet happened, okay? Now, the important thing is we need to be able to take these deaths. We don't have deaths in our graph. We just have R for removed, okay? So we need to somehow relate the deaths to the amount of people who will be removed from the infected, from the susceptible population, actually. What I did, first of all, is I just created a new matrix, R data, where I just took the deaths information, the weeks and the number, and put it in there, okay? And then what I did was, actually the way I've written this, I'm simply affecting the second, what this means is we're going to take the data in every row, okay, so that's every week, and we're going to look at the second column and we're going to manipulate it. So I need to explain what this bit of code right here is doing, okay? So let's look at the first part of that. The deaths divided by 0.02. You might realize, okay, that's 0.02%. So I'm making an assumption here. So assumption number 1 is that 2% of people who get sick end up dying of COVID-19, right? So I'm just basing that on there. If you read reports that they're all over the place on what that number might actually be. The problem is nobody really knows how many people have been sick because testing is limited. So we don't really know the rate of death. And it seems to vary in some places like Italy, the number seems to be different than China. So we're getting numbers all over the place. But about 2% of people would die. All right, so let's just say in a week where, let's just take this week right here, where 1,709 people had died. Okay, what we can do is we can figure out, I'm going down to the command window here. If I took 1,709 and divided by 0.02, I get a number of 85,450. Now, what would that number mean? Well, if 1,709 people have died, and that only represents 2% of the sick population, it means 85,450 people must have been sick at some point in order to have 1,709 deaths, all right? So what we're going to assume is that means there were 85,450 people who have been removed from the susceptible population. 98% of those recovered. 2% of those died. So that's where the 1,709 comes in. It would be 2% of the 85,450. But we're working backwards. We're going to take the number who have died and figure out how many must have been removed from being sick based on that. Okay, so dividing by 0.02 is revising upward to how many people had actually passed through being ill, and 98% had recovered and 2% had died. So that gives me a number on how many have been removed. So that gives me a proper R value to use, okay? Now, the next thing that happens is we divide by 9E6. 9E6 is another way to say 9 billion. And that's my second assumption, that 9 million is the population of New Jersey. It's more like 8,800,000 and some thousand, but we're close enough to 9 million that we'll use the 9 million number. All of the data in our chart is based on proportions. 1 means 100%. So we don't want 85,450 showing up on our chart. In order to plot data, we have to take the answer that we just got and divide by the 9 million people in New Jersey. And it would tell us that that means less than 1%, almost 1%, if I look at this number, almost 1% had been sick at that point. Okay, so that's a more realistic number. Okay, so as a proportion, when we look at numbers, sometimes they seem very large. 85,000 seems like a huge number of people, but it's only about 1% of the population of New Jersey. So we need to divide by the 9 million to bring everything back into the proportion of the population in New Jersey. So that's what this line of code is doing. Okay, now this line of code is going to be plotted, this R data is going to be plotted in plot choice 4 or case 4. Okay, so when I get to case 4, you can see I plot T versus R as always, but I also am going to plot this data that we just created, well, the data we took and manipulated with that, along with that. So let's see what happens when we plot graph 4. Okay. So here we go, plot choice number 4. And let me make my graph a little bit bigger. You can see those little stars are the actual data points. Okay, so based on the number of deaths, that is the number of people who should have been removed, assuming that 2% of people who became ill eventually died. So these stars represent where the data should be. We can see that we're clearly not there. Okay, so what I'll do is I'm going to stop this video, and then in the next video, we will manipulate the parameters so that the data actually does match this.